Both of these pieces of meat lost weight. Both of them look cured from the outside. One of them is. The difference is not what was in the meat. The difference is the world the meat was placed into while it dried. The temperature, the humidity, the air around it. That world is what this episode is about. Hi, this is the Curesmith and welcome to From Zero. Long before anybody had a thermometer or a hygrometer or a curing chamber fitted with a digital controller, people already understood something very practical. Salted meat behaved differently in different places. Leave it in the wrong environment and it's spoiled. Hang it in a cool cave or a subterranean cellar after salting and something very different happened. The meat continued to lose moisture slowly. It became firmer over time. The flavor deepened. It lasted, sometimes far longer than anyone had reason to expect. They did not have the language we use now. They were not measuring water activity or relative humidity, but they were observing reality carefully, and what they observed, they passed on. The cave did something specific. It was stable. The earth and rock surrounding it acted as a thermal buffer in both directions, cooler than the outside world in summer, but warmer than the outside world in winter. In the depths of the European winter, a cave or a cellar could sit several degrees above freezing while the air outside was well below it. In the heat of summer, that same space remained cool while the world above it baked. The result was not simply cold, it was consistent. And because of the soil, rock and moisture surrounding that cavity, it held a reliable level of humidity that prevented the outer surface of the meat from drying too quickly. Cool enough to slow spoilage, humid enough to allow even, gradual drying, stable enough to let time do its work. That is the beginning of microclimate, and it is still the model today. The cave was not magic, it was doing something measurable, and we now understand exactly what. We now understand the mechanism those early curers could only observe. Meat that has been salted begins losing free water through osmosis. As that free water is drawn out, water activity drops, and the environment for microbial activity becomes progressively less hospitable. But that process takes time, and during that time, the meat remains vulnerable. Temperature is one of the tools we use to manage that vulnerability. On screen, you can see the growth temperature ranges for the key organisms we are most concerned about in dry cured meat. Salmonella, Clostridium botulinum, Clostridium perfringens, Staphylococcus aureus, Campylobacter, Listeria, E. coli, Shigella, Bacillus cereus. Look at the optimum column. Most of these organisms grow best or near body temperature, between 35 and 42 degrees. But the danger zone, what I like to call the red zone, is really between 18 degrees centigrade and 52 degrees centigrade. This is the temperature band we are trying to avoid at all costs. For dry cured meats, we don't want to cook the meat, so it means moving the meat below the range slows their activity significantly. But here is the point I want you to hold on to. Temperature does not stop microbial activity entirely. Listeria octogenus can grow at minus 0.4 degrees. Non-proteolytic Clostridium botulinum can grow from 3 degrees. Keeping meat cold buys time. It does not eliminate the risk. Refrigeration is not a kill step. It is a slowing mechanism, and that buys time for the other hurdles to do their work. This is a multi-hurdle system. Temperature is one lever. Salt, water activity, hygiene, and ratio consistencies are some of the others. Remove any one of them and the system is weakened. The cave was not protecting the weak simply because it was cold. It was protecting the meat because the cold gave the salt time to do what the salt needed to do. What the cave was providing without anyone knowing the mechanism was a controlled microclimate. What we're talking about is the specific controlled environment immediately around the meat. If you've been watching this series from the start, you'll recognize the Curesmiths Temple, the foundation, the pillars, up to the top of the roof, the safety triangle. In episode 3, we dealt with the first corner of that roof, water activity. Today, we're dealing with the second corner, microclimate. 3 variables make up the home curing microclimate: temperature, relative humidity, and air exchange. Get all 3 right, and the meat dries as it should. But get any one of them wrong, and the consequences range from a ruined product to a dangerous one. This episode is about understanding all three. What our forebears built from instinct, we are going to build from understanding. Before we go any further, I want to draw a distinction that is often misunderstood. Curing and maturing are not the same thing. They happen in sequence, they require different conditions, and confusing the two is one of the most common terminology errors curesmiths make. Curing is the salting phase. This is where you apply salt according to your formula or your ratio, and the salt begins penetrating the muscle, drawing out the free water and starting the reduction of water activity. The curing phase belongs in the refrigerator. Just a quick note on terminology in US regulatory language. The FDA defines curing specifically as the use of nitrate or nitrite. Salting alone is technically classified as preserving. That distinction matters in a commercial and regulatory context, and I want to flag it because someone will bring it up in the series. And in the broader international charcuterie tradition, we use the term curing in its wider sense, the salting stage with or without the addition of nitrate. When nitrate and nitrite is involved, I will make that explicit. Maturing is what happens after the salting is complete. The meat has been cured. Now it needs to continue losing moisture slowly and evenly over an extended period. This is the drying and flavor development phase, and it requires a different environment entirely. 2 phases, 2 environments, 1 product. Knowing which phase you're in is really very important. Once the curing phase is complete and the meat moves into the maturing environment, the temperature range changes. The accepted range for maturing dry cured meat is between 8 and 18 degrees Celsius, but I do not want to leave you with that range without some context. The popular widely accepted working range within that is 10 to 14 degrees Celsius. That is where most home curing guidance will direct you, and it is a sensible starting point. Between 14 and 16 degrees, the pressure on the multi-hurdle system starts to increase. Microbial activity becomes more active. The other hurdles, salt, reduced water activity, and hygiene, have to work harder. For thin sausages with good salt penetration and a short maturation window, this may be manageable, but for larger whole muscle cuts, particularly with a bone through the center, it is not a risk worth taking. Above 18 degrees, the risk profile changes significantly for most products. That is not a safe working temperature for home maturing. For a standard home curing chamber setup, 12 to 14 degrees Celsius is the commonly accepted working target. It sits in the conservative middle of the accepted range, not so cold that the drying stalls for most products, and not warm enough to place unnecessary pressure on the safety hurdles. Now I want to spend a moment on something that most online guides do not cover, and that I think deserves to be taken seriously. Some experienced curesmiths mature at temperatures between 3 and 8 degrees Celsius, what I would call cold maturation. The claim they make is that the quality of the finished product is far superior. Finer texture, more complex and restrained flavor, a generally cleaner result. The science behind this is real. Flavor development in dry cured meat is driven by 2 groups of enzymatic processes. The first is proteolysis, the gradual breakdown of muscle proteins by naturally occurring enzymes, producing the small peptides and free amino acids that are the direct precursors to flavor. The second is lipolysis, the breakdown of fats by lipolysis, producing free fatty acids and volatile compounds that contribute to aroma. Both of these processes are temperature sensitive. They slow at lower temperatures, but slower does not mean less. What lower temperatures appear to produce over a longer maturation time is a more controlled and even enzymatic activity, with less risk of the kind of accelerated breakdown that produces off flavors at higher temperatures. The practical result, cold, slow maturation tends to produce a subtler, cleaner flavor profile than faster, warm maturation. The standoff is time. A product maturing at 13 degrees in 4 months may need 8 months or more at 5 degrees to reach the equivalent state of development. Some practitioners consider that worthwhile, others do not. The standard range is where you start. Cold maturation is a direction worth exploring once you understand your chamber and your products. A question that every beginner asks, and probably reasonably so: if cold is good, why not simply leave the meat in the refrigerator until it is ready? The answer is humidity. A domestic refrigerator is designed to keep food cold. It is not designed to allow controlled even drying over weeks or months. The refrigeration cycle removes moisture from the air inside the cabinet as a byproduct of cooling. The result is the air that is cold is also very dry. In that environment, the outer surface of the meat dries rapidly, far faster than the interior can release moisture. The outside hardens, and when the outside hardens, it closes off the surface in a way that traps moisture inside the product rather than allowing it to migrate outward and evaporate. This is what we know as case hardening, and we've dealt with this before. And it is one of the most unwanted and misunderstood failures in home dry curing. Case hardening is one of the most damaging failures in home dry curing, and it is particularly insidious because the exterior of the product can appear perfectly fine while the interior is in serious difficulty. The outer layer forms a hard, tight crust, and beneath it, the remaining free water cannot escape. In mild cases, the product simply does not dry properly. Dense, uneven textures, poor flavor development. In severe cases, the trapped moisture creates conditions for spoilage to begin inside the product while the outside looks acceptable. Here is the part that catches most people out. A product can show the correct weight loss on the scale and still be case hardened. The scale measures total weight. It cannot tell you whether the weight was lost evenly while the outside dried and the inside was left moist. The goal of dry curing is not to create a dry shell around the wet core. It is to reduce moisture evenly throughout the entire piece, and this is something we're going to repeat over and over. Humidity control is what makes even drying possible. The scale tells you how much weight you lose. It does not tell you where you lost it from. If temperature is the variable most beginners think about, humidity is the one most beginners underestimate. This instinct is understandable. We are trying to dry the meat, so surely a dry environment must be better. That instinct is wrong. The outer surface of the meat must stay open long enough for moisture from the interior to migrate outward. If the surface dries too quickly, that migration is blocked. If the air is too humid, moisture cannot leave the surface at all and drying stalls. The maturing environment needs to allow drying without forcing it. The accepted range for relative humidity in a dry curing maturing environment is 65 to 80% relative humidity. My preferred working range is 72 to 75%, with 73% as a reliable average target. Below 70% begins to dry more aggressively. As the reading approaches 65% and below, the risk of case hardening increases meaningfully. Above 80%, a different set of problems emerges. Drying slows substantially, the surface of the meat may remain wet for extended periods of time, and mold pressure increases. On the question of mold, I want to be precise here, because not all mold in the curing environment is undesirable. In some long-aged products, a controlled white mold on the surface is part of the normal intended maturation process. The concern over 80% is not mold in general, it is uncontrolled mold, rapid growth of molds that have not been selected and may indicate the chamber environment is simply too wet to allow safe drying. Mold management is a full subject on its own, and we will cover it in detail in the mold control pillar of the temple. But if you're ever forced to choose between slightly too wet and slightly too dry in your chamber, err towards slightly too wet. Excess surface mold can be wiped off with a clean cloth, damped in a light brine solution, and the product can continue curing safely. A product that case hardens is far more difficult to rescue. The humidity window is not there for decoration. It is one of the main controls that determines whether the meat dries properly. There is a third variable in the home curing microclimate, and it is one of the most commonly misunderstood. And this misunderstanding carries real consequences. I want you to be careful about the language here, because the distinction matters enormously. Air exchange, not air flow. They are not the same thing. Air exchange is the replacement of stale air inside your chamber with fresh air from the outside. Over time, the air inside the closed maturing chamber accumulates carbon dioxide from the natural microbial activity on the surface of the meat. Fresh air restores the balance. This is the renewal the chamber genuinely needs. Airflow, on the other hand, is directed movement of air across the product surface itself. This is categorically different, and it is another cause of case hardening. And here is why. In still air, a thin layer of humid air naturally forms on the meat surface. That layer moderates evaporation, limiting to roughly the rate at which the meat can release moisture from the interior. Still air is not a problem. In a well-managed home chamber, it is often closer to the ideal condition than most beginners realize. Direct airflow strips that protective layer continuously, driving surface evaporation beyond the rate the interior can sustain. Case hardening follows. No fan belongs in the home curing chamber. I want to explain why, because the advice to add a fan appears everywhere online and it is not wrong in its original context. Commercial curing rooms can be 150 cubic meters or larger. In a space of that scale, without mechanical air management, you get dead zones, areas where temperature and humidity diverge significantly from the rest of the room. A commercial fan, properly positioned, addresses that real problem. A home chamber is an entire different environment. A typical converted fridge for home curing holds between 1 and 2.4 cubic meters. In that space, temperature variation between the top and bottom of the chamber is typically 0.3 to 0.5 degrees Celsius. Humidity variation might be 1 to 2%. Neither of those differences will change the outcome of the meat. They are within the natural tolerance of the process. A standard 80mm computer fan moves approximately 55 cubic meters of air per hour in a 1 cubic meter fridge. That fan turns over the entire chamber volume 55 times every hour. The problem a fan exists to solve does not exist in a home chamber. The problem a fan creates, relentless air movement across the product surface, is very real. The commercial airflow guidance most home curers are reading was written for rooms between 60 and over 1,000 times larger than a converted fridge. The science is real, the context it was written for is not yours. So what does the chamber actually need? The air exchange a home chamber needs is most certainly already happening. If you open the door daily or every other day to inspect the meat, those few minutes replace the stale chamber air with fresh air entirely. Monitoring and air renewal happen at the same time, with no additional equipment required. Now, to check whether any unwanted airflow is reaching your product, use the simple paper strip test. Take a strip of paper or a short length of thread or string and hang it at meat level in your chamber. Close the door and allow the chamber to run normally. And if that paper moves, if there's any visible movement at all, you have meaningful airflow at product level. That is not the goal. It is a warning sign. Find the source and eliminate it. And if your refrigerator has an internal fan for cold air circulation or any other equipment in the chamber that produces air movement, redirect that airflow away from the product. Baffles, repositioning, a physical barrier between the fan and the hanging meat. The objective is zero air movement at product surface level. For the full treatment of the fan question, including the full volume calculations, I've covered this in detail in a dedicated Curing Questions Answered episode. I will link that below. Air exchange is opening the door. Airflow is what ruins the meat. Before adding anything to your curing setup, I want to give you a framework that'll serve you for every decision you make about this chamber, now and in the future. 2 questions. The first is, what specific problem does this item solve in my particular setup? Not what might it improve, not what do other people use, what specific identifiable problem does this address in my chamber? Second, does it create a problem larger than the one it solves? If you apply those 2 questions consistently, they will save you significant, unnecessary expense, and they will protect you from the equipment-related failures that cause a disproportionate share of home curing problems. Take the dehumidifier as an example. It appears in almost every home curing setup guide online. Most people add one because they've seen others add one, not because they've identified a specific humidity problem their chamber cannot manage without it. A dehumidifier is a legitimate piece of equipment in 2 specific situations. A chamber operating in a very high ambient humidity environment where the chamber simply cannot maintain an appropriate internal relative humidity without assistance, or an older type refrigerator with an evaporator plate that causes condensation when running above 7 degrees, creating humidity spikes. In a frost-free refrigerator operating in a moderate climate, a dehumidifier is not needed. Adding one unnecessarily introduces a mechanical element, an additional power draw, and an additional variable without solving any real problem. And the same logic applies most forcefully to the fan. It solves a problem that does not exist in a small chamber and creates one that can ruin months of work. A chamber that works is not the most elaborate one, it is the one where every element has a clear reason for being there. We will come back to this framework in the chamber building episode later on in the series. But I introduce it here because microclimate is where the consequences of equipment decisions become visible. Every piece of equipment you add either supports your control over temperature, humidity, and air exchange, or it interferes with it. Complexity without understanding is not control. It is more variables you cannot account for. Once the standard principles are well understood, the exceptions become interesting rather than confusing. San Daniel prosciutto is one example of the exceptions. In the San Daniel region of northeast Italy, some producers maintain relative humidity in their maturing rooms well below the standard range, in some cases reported to be as low as 50% relative humidity or below. At first reading, this appears to contradict everything in this episode, but in practice it does not. The producers of San Daniel prosciutto are making a single specific product in a facility purpose-built for exactly that product, using a tradition of knowledge and infrastructure that has been refined over generations. Their rooms are not set up for coppa, pancetta, lonza, or salami simultaneously. They are optimized for one product. The lower humidity in some San Daniel facilities is understood to affect the color development of the finished product. Higher humidity can produce a deeper red in the lean, which is considered undesirable in San Daniel prosciutto, but would be perfectly acceptable in other whole muscle products. For the home curer, with one chamber and a range of different products, the San Daniel exception is not a model to follow. It is an illustration of how deep expertise and dedicated infrastructure can operate in a narrower band than the general guidance recommends. Now consider biltong. The traditional South African dried meat operates by a fundamentally different method. The meat is cut thin, marinated or salted, and then dried rapidly with direct airflow and sometimes with gentle heat. The goal is fast dehydration, often within 48 hours. The product, the process, the risk profile, and the microclimate are all different from European slow-cured whole muscles. American beef jerky is a further variation, typically involving heat as part of the dehydration process, which adds a lethal treatment that slow European-style cured meats does not rely on. These are not exceptions to the principles of microclimate. They are examples of different principles applied to achieve different outcomes. Applying biltong methods to prosciutto or prosciutto methods to biltong will not produce either product correctly. Different product, different method, different microclimate. The principles are consistent even when the parameters are not. Always ask why a method works before deciding whether it applies to what you are making. Now let us bring this all back to the Curesmiths Temple. Microclimate is the second corner of the roof. It does not replace water activity, and it does not compensate for insufficient salt, poor hygiene, or incorrect ratios. What it does is create the conditions under which water activity can fall safely and evenly, where time can do its work properly and where the other hurdles remain effective. Remove microclimate from the system, cure in a domestic refrigerator with no humidity control, and case hardening becomes likely. Microbial risk inside the product increases. The reduction in water activity that should protect the product becomes uneven and reliable. The cave was not magic. The cellar was not magic. They were providing, without knowing the mechanism, the same conditions a controlled maturing chamber provides today. Stable temperature, buffered from the extremes of the world outside, humidity at the right level, undisturbed conditions for as long as the product needs. In episode 5, we complete the roof of the Curesmiths Temple by examining the third corner, pH, acidity, fermentation, and why some cured products depend not only on drying, but on controlled acidification working in concert with everything this episode has established. Because safety is not one thing, it is the triangle, and every corner matters. See you in the next one.